Good evening, all. Welcome to Unacademy. Okay, let's wait 2 minutes, then we'll start the session. Okay, listen. My name is Bhanu Prakash, expert in GATE and ESE. I did MTech from NIT Kurukshetra. I have 10 years of teaching experience and I train many students throughout our country for different competitive exams like GATE, ESE, Transco and Genco. My subjects are electrical machines and power electronics. BPC 10 is my code. Okay, if we use this code, you will get 10% discount on Unacademy plus subscription. Okay, and what are the benefits? What are the types of the subscription? There are the two types of the subscription. One is a plus subscription. Okay, in case of the plus subscription, what are the benefits? One is a live classes. Okay, you will get live classes from top educators of the country, and similarly you will get structural schedule. Okay, this schedule for 3 months, 6 months, 12 months, 18 months, like this. And also you will get unlimited practice questions for subject wise and also topics wise. And one more benefit of the plus subscription, that is the test series. So and next one, this is a iconic subscription, is a so complete package of all the these four subscription, and also in addition to these four you will get some other the subscription some other benefits. One is a we will assign personal coach, so he will guide everything until you get the job or until you get the admission in the any prestigious college in India. And also this is the study planner. Okay, exactly, we will provide complete study planner and also course material. Everything we will provide based in case of the study planner. And also expert guidance, you will get expert guidance of any competitive exam. Suppose if you want to write GATE, so what are the expert guidance of the GATE? You will get all these things, and also you will get ESC questions and answers. So we will provide everything, all practice questions and also answers for this question. These are the benefits of iconic subscription. Okay, all of it clear? Yes, good evening all. Ready, Pavan, Isha, Siddhant, Bhargav, everyone. Good evening, all. Okay, listen. So, this is the new fee structure of the iconic and also plus subscription. So, per plus subscription, this is the 2 month subscription. So, after using my code, that is the BPC10, so you will get 10% discount. So, after the discount, you have to pay 27,000. Okay, 27,225 rupees. Okay, this is the new fee to get the 1 year subscription, 1 year plus subscription. And this time we are introducing new plan for 18 months. So for 18 months the fee structure is a 34,650 rupees. Okay, after using my code, okay, here using my code you will get the 10%. So after the 10% discount, you have to pay 34,650 rupees. And also 24 months also available for this the plus subscription is available for 24 months. So what is the fee structure? That is 39,600 rupees after using my code BPC10. So if you use this code, you will get 10% discount here. Now similarly, one more subscription, that is a iconic subscription. It is available for the 12 months and 24 months. So what is the fee structure for the 12 months? 40,500 rupees. For this the 24 months, what is the fee structure? 54,000 rupees. Okay, so this is the plus subscription and iconic subscription. All of you got it? So are you clear about the new fee structure for the plus and iconic subscription? Joseph, good evening. Okay, all of you clear? Everyone? Okay, listen. Previous class we had discussed about copper losses of transformer. So what is the mean by copper loss of the transformer, and how do we calculate the copper losses of transformer? And after that we had discussed about iron loss of transformer. So this iron loss are two types. So one is a hysteresis loss plus eddy current loss. So we have discussed about the hysteresis loss point of view. The hysteresis loss occur in the any magnetic material due to reversal of magnetization when alternative nature of the flux is passing through it. If the flux is a DC nature, there is no hysteresis losses in the magnetic material here. So again, after that we have discussed about the what is the formula to get the hysteresis loss. WH is equal to KH B maximum power of 1.6, the F multiplied by V. F is a frequency and V is a volume of the core. So during operation, okay, this is a during operation of the transformer, the hysteresis loss directly proportional to the product of the flux density and frequency of the transformer. When B maximum is constant, there are the two cases. Okay, when the B maximum is constant, so what will happen? The hysteresis loss directly proportional to frequency. The when B maximum is not constant. Okay, when the B maximum the is not constant, so this is a the hysteresis loss directly proportional to V1 power 1.6 and inversely proportional to F power zero point 0.6 here. So this part we have discussed in the previous class. Got it, fine? What is the relation between the hysteresis loss and frequency? When B maximum is constant, the hysteresis loss directly proportional to the frequency. When B maximum is not constant, that is a variable, the hysteresis loss directly proportional to V by F ratio. Okay. Okay, is that clear, everyone? Very good. So today we will discuss about another law, that is a this eddy current losses of transformers. Okay. So here we have some questions like first one. So that is a what is the reason? So what are the questions here? So there is a one question like, so that is the what is the reason to get the eddy current losses? Okay, this is the what is the reason, the here what is reason, okay, to get the eddy current losses of transformer. Okay, here what is the basic reason to produce the eddy current losses in a transformers. Okay, and next one, so we have a question, what is mean by eddy current losses? Okay, this type of the question. And next one, how do we calculate? Okay, this is a how do we calculate eddy current losses of transformer. So these are all possibility of the questions. Okay, all of you clear my point? So what this is the first question is, what is the basic reason to get the eddy current losses of the transformer, and also what is mean by eddy current losses. And third one is a how do we calculate the eddy current losses of any magnetic material or any magnetic core or transformers. Okay, the initially we will see here first one. We know that before going to the discussion about eddy current losses, so let us discuss about the types of the material. Okay, this is a, so there is a small discussion. So that is a types of the material in the electrical system. Okay, this is the materials the in the electrical the system. So what are the types of the material in the electrical system? So one is a first one, it is a magnetic, sorry, the first one is a electrical materials. Electrical material. So electrical material, so what is the example for the is this electrical material? The example is a copper or aluminium conductors. Okay, all the electrical material. And second one is a the in this is the magnetic material. What is the example for the magnetic material? So this, let us take the silicon steel materials. Okay, this is the example for magnetic material. Next one, third one is a insulating material. These are the materials in the electrical system. Okay, insulating material and also electrical material. Okay, what is the example for this insulating material? Any insulation, mica insulation, red oxide paints. Okay, here mica insulation or any paints, that's all are the insulating materials here. So question is, what are the properties of these electrical materials here? First property, see, electrical material. So any electrical material has the conductivity. So conductivity is a very high value of the conductivity. So now this conductivity is a very high value. So but what about the permeability of the electrical material? So this permeability of electrical material is equal to 0. So this is a permeability is equal to 0 in case of electrical material. And next one, what about the magnetic material? So conductivity here, permeability is a very high. Suppose in case of the silicon steel, permeability is very high. And what about the conductivity? It has very small value of the conductivity. Very small value of conductivity. So next one, so insulating material, permeability is equal to 0 and also conductivity is equal to 0. So what about this part? Okay, here see, the in case of the magnetic material. Okay, magnetic materials here. So what it means, that any magnetic material act as a conductor with small value of the conductivity. So what we conclude here, so what is the conclusion of this discussion? So that is a, yeah, any magnetic material, any magnetic material act as conductor, conductor with small value of conductivity. Okay, so any magnetic material act as a conductor with small value of the conductivity here. Suppose it is a transformer core. Okay, this is a completely transformer core. So this core has high value of the permeability. and low value of the conductivity, so that it act as a, okay, here act as the conductor, okay, conductor with small value of the conductivity. So what will happen, it allows the current, some value of the current, okay, as like a conductor, copper wire or aluminum conductors, okay, all of clear point. So any magnetic material act as a conductor with small value of the conductivity. Are you clear up to now, everyone? Yes, yes or no? Very good. Here, so whenever transformer, okay, or any magnetic core excited with the AC supply, okay, this is the AC supply, and time varying nature of the current, I know magnetizing current, I know is equal to Im sin omega t. Okay, time varying nature of the current passes through here. So due to which time varying nature of the flux produced in the primary event. Suppose let us assume this is the current entering position and this is the current leaving position like. So what will happen? Flux direction. This is the direction of the flux. Okay, this is the direction of the flux here. So flux pi of t, okay, passes. So which also links in the secondary winding the through transformer core. Okay, this part we have discussed already. So whenever time varying nature of the current passes to the winding, time varying nature of the flux will be created in the primary winding, which also links in the secondary winding through transformer core. So here core contains the time varying nature of the magnetic field. All of you clear point? And also this is the act as a conductors. So what will happen whenever time varying nature of the flux links with the conductors? Actually, here EMF, this flux will induces the EMF in the primary winding as well as the secondary winding of the transformer. So in addition to these two EMF, some small amount of EMF induces. Okay, this is the small value of the EMF induced in the core. Okay, this EMF is known as, that is the EMF induced in the core or magnetic core or transformer core. So this induced EMF gives rise to the circulating current. So within the core, so that current is known as a eddy current, and power loss due to this current in the form of heat due to temperature rise is known as eddy current power losses. Okay, all of it clear my point? Okay, shall I repeat? Yes. Okay, see here. So initially what will happen, first one, that is a AC supply. Okay, the one by ones, the AC supply, the core is excited with the AC supply. So due to which what will happen, current passes through, which current here, time varying nature of the current in winding of transformer. Okay, in the primary winding of the transformer. So after that flux will be created. Okay, this is the phi of t, the flux created in primary winding. So this flux links, okay, with the, okay, this is the flux the created, the pi of t created in primary winding. primary winding and passes through, okay, this is the passes through, okay, which one? The transformer core. Okay, this is the passes to the transformer core. So after getting flux here, so this is actually this flux here, okay, induces the EMF. Okay, this flux induce, okay, induce the EMF in primary winding and the secondary winding. Okay, what is the reason? So this flux links with the number of the turns. Okay, that is the E1 is equal to the N1 d phi of t by dt. Okay, this is flux links with the number of turns of the primary winding, so that EMF induced in the primary. Now similarly, this flux links with the number of turns of the secondary winding, so that is equal to d phi of t by dt. So this is the secondary induced EMF. So these two EMFs are called, that is in winding EMFs. Okay, winding the EMFs of transformer here. So this part already we have discussed in case of operating principle of the transformer. But what will happen? See, the same flux, okay, here, so links with the core. Okay, this flux, the when links with the core, whenever so links in the core, okay, transformer core. So that is why, because it acts as a conductor. What are the basic requirement to induce the EMF? Magnetic field, set of conductor, relate to time variation between the magnetic field line, set of conductor. So whenever it links in the core, so EMF induces in the core. Okay, that. So therefore that EMF is equal to, core is it is act as a 1 ton, so that it is equal to, so d phi of t by, okay, dt. So this core, okay, gives rise to circulating current. Okay, this is gives rise to the circulating current. So current in the core, okay, the circulating current is nothing but I square R current in the core. So this circulating current the causes some amount of the power losses in the form of the heat. Okay, this power losses is known as eddy current power the losses. Okay, this is the exactly meaning of the eddy current loss. Okay, Pawan, what's your question? Sir, if eddy current is more than the insulation convert to conduct. Construction లో కూడా డిస్కస్ చేశారు సార్. Yes, I have discussed in the construction details also, but today I will discuss in very details manner. Okay, one of the clear point. So this is the eddy current losses. How do we define the eddy current loss? Eddy current losses occur in the any magnetic material due to the extra EMF in the core in addition to winding EMF. So which in turn produces the circulating current. So power loss due to this circulating current, so is known as a eddy current power losses. All of it clear? Everyone. Suppose see this example point. So I will tell you one real time example. So about the eddy current loss. Okay. So see here. This is the one river. Okay. It is a river. The flows. Okay. This is a water direction. So this is the direction of the water. The water directions like. This is the direction of the water. Clear point? So here I am showing it is a direction of the water. Okay. So just like, okay, this direction of the water means just like current in the core, current in transformer core. Okay, transformer core like. So what will happen? Some part of the current, okay, here current here transformer core. So here this part, okay, what is the mean by eddy currents here? Actually, water flows from left to right in the river, but at some places there are some eddies. Okay, that is a, so this is the water current, the water eddies like this. Okay, this is the water eddies. So here it is opposes the flow of the current. Simply only flows at this only one point. So now this is nothing but, okay, here the water eddies. Okay, this is a water eddies like. So now here current flows in the core, but suppose if we take, okay, this is the one magnetic material. Okay, here any magnetic material. So what will happen? Some part of the current, okay, within the core like this, okay, within the core. So these currents are known as a the eddy currents. Okay, eddy currents here. Suppose here is a, if it is the area of the this the plate, or either this is the thickness or the layer, or the this is the magnetic core here. So this magnetic core area can be reduced by half, or thickness is reduced, so that you can reduce the this is the eddy currents like. So all of you clear point? Do you want to zoom? Okay, so all of you clear? Eddy current in the sense, okay, suppose తెలుగులో వాటర్ ఫ్లో ఉంది అనుకోండి ఒక రివర్ లో, ఆ రివర్ లో వాటర్ సుడిగుండాలు ఉంటాయి కదా, దాన్ని వాటర్ ఎడ్డీస్ అని అంటాం. సో సిమిలర్ వే some amount of the current in the core, the eddies, okay, so which that power loss due to this current, circulating current, is known as a eddy current power loss. So this water eddies is nothing but similarly. So this one is a, that is a circulating current in the core. Circulating currents in core. Alafi got it point? Exactly meaning of eddy current. Eddy current means circulating current. Some part of the current circulated within the core. As like some part of the water circulated within the river. Okay, here within the river. Actually, river flows from left to right. But some part of the water circulating within the river. So it is a similar way. Some part of the current circulating within the core. So that current is known as eddy currents. And power loss due to this eddy current is known as eddy current power losses. Okay. All of you got it, everyone? There is a question we have. So why it is circulating? Just like a water river. So in the river, some part of the water circulating within the river only at one point. So that is known as water eddies. Now similar way, currents also circulating at some portion, okay, some unit volume of the core. So that currents are known as eddy currents. Sir, if eddy current is increases, then both windings are not isolated. Direct current flow through the 1 and 2. No. Actually, there is an insulation between the each laminated part. So here, how do we reduce this one? So this is the complete part. Suppose if I make it is, okay, it is a some insulation. Okay, this is a some insulated part. Okay, like, so this is the, we have taken as the insulation part. So what will happen? This insulation we are providing. Okay, insulations are provided. So therefore, eddy current flows within this region, only one circulating current. So that's why we can minimize the circulating current. Okay, minimize. So we can by laminating the core. All of it clear, everyone? So that how do we write how do we define the eddy current loss? So here eddy current loss, the eddy current loss occurs in the any magnetic material, occurs in any magnetic material due to finite value of conductivity of the core, finite value of conductivity, value of conductivity of the core. Okay, got it? So when time varying nature of the flux is passing through transformer core, EMF induced in the core, EMF induced in core, due to which induced in the core, due to which circulating current will be formed, power loss due to the circulating currents, power loss due to this circulating current is called eddy currents, eddy current power loss, eddy current power loss. All of it clear? How do we define the eddy current power losses here? Eddy current, basic reason to get the eddy current is finite value of the conductivity. So whenever time varying nature of the flux is passing through the transformer core, EMF induced in the core, which in turn produces the circulating current. So power loss due to the circulating current. This is the power loss. So due to circulating current in the form of the heat. Okay, here. So in the form of heat. So these power losses is known as eddy current power losses. Joseph, it cannot opposes this only circulating within the core. Just I am taking one example here. The example that is the water in the river. Okay, water flow in the river. I have taken water flow in a river. So what will happen? Some part of the current circulating in the within the river. So that is known as a eddy, water eddies. Okay, that is a similar way. Some part of the current circulating within the core. So that currents are known as eddy current. And power loss due to that eddy currents in the form of heat due to, so that power losses is known as eddy current power losses. Okay. All of it clear? Everyone. What is the mean by eddy currents? Now onwards, you don't have any question about the eddy current, I think. Am I right? Have we clear everything about eddy current loss? So if any question asked in the interview, what is the basic reason to get the eddy current loss in the magnetic material means? What is the basic reason? Finite value of the conductivity. This is the basic reason. Finite value of conductivity. So any magnetic material act as a conductor with small value of the conductivity. So this is the basic reason to get the eddy current losses. Eddy current losses can be minimized by reducing the conductivity, but you cannot nullify. What is the reason? Any magnetic material act as a conductor with small value of the conductivity. Okay, clear everything? Yes. Yes or no? Siddhant, thank you. Okay. So now question is, how do we calculate? This is a very important. How do we calculate eddy current loss? Okay, so let us assume this is a exactly one, okay, this is a one limb of the core or one yoke of the core here. So this is a, suppose here this is the direction of the, all the direction of, okay, this is the direction of flux lines. Suppose flux lines are passing in the core like this. Okay, this is the all the flux lines. So what will happen? See, so this is the phi of Tn, direction of the flux here. It is the one magnetic core. So this is the length of the plate. Okay, this is the length of one plate. Okay, here we have taken one single plate. So now next one. So this is the length of the plate, and this is the height of the plate, right? So it is the height of the plate here. So now this complete this part, it is a thickness of the plate. Okay, like, so for our convenience I have taken, so thickness is a very large amount. Actually here thickness is a very small as compared to height. So for the diagram point of view I have taken here very large amount. So what about the circulating current? Okay, this is the first circulating current. Okay, like this. Okay, here some circulating current, the flows, okay, like this. These are one circulating current, and next one another circulating current, okay, like, and another one another circulating current. So these are the circulating currents within the core. Okay, within the core. So clear point. Okay, this current is known as a the eddy current. Okay, eddy currents here. So all of it clear. So this is the magnetic core. Okay, here magnetic the core here. So whenever alternative nature of the flux is passing to the magnetic core, some EMF induces in the core. So this EMF, okay, EMF gives rise to the circulating current within the core. Okay, these circulating currents are known as eddy current, and power loss due to this circulating current in the form of heat is known as a eddy currents. Okay, eddy current. How do we calculate eddy current loss? Suppose, let us initially what we have to do, first calculate area of the first eddy currents. Okay, this is the first one, and integrate this one, you will get complete the eddy current loss. Okay, as like instantaneous power, energy loss, and also integration, that you will get the complete power losses here. Now similar way, so this we have taken, this is a, it is a the here B, and this is the CDL. So for our convenience, I have taken like this. Suppose here ABCD is a, okay, one the circulating current. That is a small circulating current here. Okay, and next one the of another circulating current, and another circulating current, and so on. Okay, like this. So this is the where H is the height of the magnetic core. So this is the height of, okay, it is a height of the magnetic plate or magnetic sheet. Okay, this is the magnetic sheet, and length is a here L is the length of the magnetic sheet. So where T is the thickness of the sheet. Okay, it is the thickness the of the sheet here. Okay, got it. So our plate or the sheet. Okay, these are we can write plate and also are the sheet like this, and here also H, and this is the total thickness T, and here we have taken this is the dx. Okay, this is a x distance x here, and this one is a dx values here. What is the mean by dx? Okay, here let dx in the sense the smallest change in the thickness. Okay, this is the smallest. Okay, let assume the smallest change, the change in thickness from the distance x. Okay, this is at a distance, smallest thickness here at a distance x, x from origin. Okay, this is the dx value here. So got it. This is the smallest the thickness, the change in the smallest thickness from the distance of the x from the origin here. So this part we have taken as the origin. Okay, like this. So this is the exactly some elemental the changes of the circulating current. All of it clear my point. Then how do we calculate? Okay, this. First one, tell me what is the area of this, okay, current path. Okay, this is the area of, okay, here the area of path of current path of A B C D. Okay, A B C D A. So now this is equal to, so what about this area? It is equal to x. Okay, and this is the h. Okay, this is the distance is the h. So that's why it is equal to 2 times of the hx. Okay, and this is the area here. So we know flux density, or this is the flux passes through. Okay, this is the flux the passes through the area of the through area of ABCDA sheet. Okay, we have calculated ABC. So now this is equal to B maximum. So 2H here. Area is equal to, so now this is a area B maximum multiplied by area. So therefore this area we can write B maximum into 2HX values here. So this is the area here. So we know that this is the first, let us take one circulating current and integrate, you will get the complete the power loss due to the circulating current. So now next one, let us take, so we know the here EMF induces, okay, EMF induce. Okay, the EMF induces is equal to how much? Okay, root 2 times of the phi. Okay, this also 4.44. The phi B maximum F the L B maximum A L area of, okay, this is the area of ABCDA. Okay, ABCDA multiplied by frequency. How many number of tons? Only 1 ton. So this is simply core act as a, here the core act as a 1 ton. That's why we have taken as a 1 ton one. So now simplify this one. So that is the root 2 phi B maximum, the 2hx multiplied by f values here. So this is the EMF induces in the core. Okay, next one. The we required the circulating current. Okay, that is a, so current the this the in this area. Okay, here current the this one is a power loss. Okay, it is equal to the power loss. Okay, per sing. So per this area here power loss. How do we calculate? That is a I square R. So this I square R we can write the VMF induced in the square divided by the resistance of this, okay, resistance of this path, okay, resistance of the current path, okay, like. So therefore this is equal to, okay, here EC we can write So that is the root 2 phi b maximum, the 2hx multiplied by f. Okay, divided by the resistance of the path. Which path here? The A, B, C, D, A. Okay, this is the resistance of this path here. So now how do we calculate? Okay, this is the resistance where resistance of this path is equal to. So how do we calculate? So that is the rho L by A. Okay, here. So that is the A length of the current path. Okay, length of this current path divided by area of this current path. So how do we calculate this length of the current path? Okay, see in this diagram. So it is a length, it is a x, okay, it is a h and it is a x, the again x and so that is equal to 2h plus 4x. This is called the length, and area is equal to here h multiplied by, we are calculating only small current, okay, small changes in the thickness. So now h multiplied by dx1. So then integrate, you will get complete area here. So that's why we can write, so this is equal to rho, and it is a 2h plus 4x divided by the length L and distance, length and width is the thickness is the smallest thickness is the dx values here. Now simplify this, okay, you will get here, okay, this is equal to square. So now this is the square values here. So now simplify, okay, this value. So it is equal to, it is a 4, the sorry, the it is equal to, simplify, the root 2 is a 2 phi b maximum square. Okay, it is equal to 2h hx. Okay, this one is a 2h x whole square, okay, whole square f square. So divided by, okay, this is equal to the root 2h the plus 4x divided by L dx. Okay, L dx values here. So now again you can simplify this. So it is equal to, this is a, this 2h value is a very high, so as compared to the 4x. Okay, why? Because it represents the thickness. Okay, this one is the thickness of the laminated sheet. So that here, so in the denominator term, 4x is a neglected here. When it is neglected, this is equal to 2 phi square. Okay, 2 phi square b maximum square, the 2hx whole square f square, the f square multiplied by L dx. So divided by, okay, this is the divided by. So now this value is equal to rho the 2h values here. Okay, 2h1. So got it point. So this 2h will be the cancelled out. Okay, this is a 2h. Okay, here 2h and here also 2h is the cancelled out, but this is the, will get the only x square terms. Okay, there is a 2, so that's why here 2 will become, okay, this value is equal to the 4 pi square. Okay, 4 pi square b maximum square, the f square. Okay, f square. So divided by rho, okay, into, so this is the x square. Okay, x square dx values here. So there is a length term, so that is equal to L values here. Okay, divided by the L values. Okay, simply I have getting mind L and H. Okay, this is the H and L values here. So now this is the, if we integrated complete value, what will happen? So by integrating, okay, by integrating, so we get the complete total, that this the, we get the total power losses. So how do we calculate this power losses here? So therefore total power loss, so that is equal to, so then you can solve this power loss, okay, by using this formula. So that is equal to 4 pi square b maximum square. So this is the 4 pi square b maximum square, the f square, the h into L. Okay, so this is the h into L divided by rho integration. Okay, integration from 0 to the t by 2. Why? Because actually 0 to x. So now this is a this one 0 to, okay, this value 0 to x square dx values here. Got it point? This x is nothing but the where x is equal to, so we have taken x is equal to, so that is a t by 2. So now substitute here. So that is a 4 pi square b maximum square f square hl. So that is a divided by rho. So that is a 0 to t by 2. Okay, x square dx values here. So now this by integration. So now here we will get 4 pi square b maximum square f square the hl. Okay, here hl values. So divided by rho. Okay, this is the divided by rho, and this one is equal to, okay, now simplify this. That is a 4 pi square x square is equal to x cube divided by 3. Okay, divided by 3 values here. So now this x cube you can write. So now the limits is the 0 to t by 2. So therefore it is equal to 4 pi square. Okay, 4 pi square b maximum square. Okay, f square h l. So now it is a t cube. Okay, the t cube divided by, okay, divided by 6 row. So now this equation you can write, okay, this equation, so that I can write here. So complete the here a total, okay, power losses. So that is equal to, how do we calculate? The 4 pi square b maximum square the f square. So that is a, this the x value. So h l t, okay, this is the thickness, the divided by t square divided by, so that is the x, the 6 row values here. So hlt means it is the volume of the volume of core, volume of the core here. So therefore that is a total eddy current loss, eddy current loss per unit volume, per unit volume. Okay, this is the per unit volume is equal to, so how do we write? That is a 4 pi square the b maximum square f square. So that is the hlt, sorry, this hlt is a unit volume. So this is a f square and t square divided by 6 row. So this you can write some constant ke. So that is the b maximum square f square and t square one. So this is the eddy current losses. Okay, all of it clear? How do we get eddy current loss? Very, very important. In the IAS, sometimes we have a question. Yes. Okay, this is the 4 will be the cancelled out. X by 2 and 4. Okay, that is the exactly we'll get the K. Ke1. Any more doubt about this? Any more doubts about what about the hysteresis loss? You can't get this one in the textbook. Is that clear, everyone? Okay, this is the divided by 24, right? X cube, and this is equal to t by 2, t by 2. So that is a cube. So divided by 24. So that here 4 into this is the 6. Okay. So that's why here we can write, okay, no need to write 4. Okay, now I think it's clear. So where ke is equal to, okay, this ke is equal to 5 square by 6 row. Okay, now it's correct, right? Isha, is it correct? Finally, ke is equal to, yes, ke is equal to 5 square by 6 row. Yeah, I have taken, actually it is a 2 only, but it's the 8. So 24, so that is equal to 6. Yes. All of you got it? Everything about how do we calculate eddy current loss. So now we have a question like, so that is a similar way, observations from eddy current loss equation. Okay. Okay, listen. So what are the observations from the eddy current loss equations here? So eddy current loss equations means we know that eddy current loss W is equal to KE. So that is the B maximum square, F square and T square here. So where B maximum is the maximum flux density, F is a frequency and T is the thickness of laminations here. This is the eddy current loss per unit volume. That's why we can write K is equal to B maximum square, F square and T square 1. So clear? So now first observation. So during the designing of the transformer. Okay, this is the during the designing of transformer. So this eddy current loss directly proportional to the T square, the thickness of the laminations here. And second one, during operation of, okay, this is the during the operation of transformer. So then what will happen? See, so during the operation of the transformer, eddy current loss, okay, directly proportional to B maximum square and F square. Why? Because so these two are constant. During the operation, we cannot change the thickness of lamination. So that's why we can write directly eddy current loss directly proportional to B maximum square and F square. So let us assume it is the equation 1. So we know during operation, okay, this way. So we know that the during operation of transformer, maximum flux density directly proportional to V1 by F ratio here. Let us assume it is the equation 2. So now substitute the equation 2. Okay, this is the equation 2. So in equation 1, okay, we get, so that is the eddy current loss, the directly proportional to V1 by F whole square multiplied by F square values here. So now this is equal to, you can simplify.
So this is the we are directly proportional to V1 square. So now where V1 is a this is the supply voltage. Okay, supply voltages here. So do here if the B maximum is constant. Okay, here B maximum is a constant. So now this is the for example, if I take so during the operation, if the B maximum is a variable, we can take this one. So this is a condition. First case is okay. It is a let us take it is a case 2 here. Okay, case 2 per. So now suppose if the case 2 means here B maximum is not constant one. Okay, that time. Suppose if the B maximum is constant. Okay, like case 1. So then what will happen? So B maximum is a constant. So when B maximum is a constant, okay, in this case, so what will happen here? So eddy current loss directly proportional to the frequency one. So here also we have a two cases. So case one is constant. So here eddy current loss directly proportional to the frequency. Eddy current loss is not here B maximum is not constant. Eddy current loss directly proportional to V1 square. All of you clear my point? Okay, next one more observation. Third one. Third one is a iron loss of the transformer. Is a very important for problem solving. Iron loss of transformer during operation. During operation here. So how do we calculate iron loss of the transformer during operation? So we know that the during operation of transformer, the hysteresis loss directly proportional to V maximum power of 1.6 multiplied by frequency. So whereas eddy current loss directly proportional to the B maximum square and F square values here. Okay, F square one. So now here case 1, okay, in this case 1. So what will happen if B maximum is constant? Okay, B maximum is a constant values here. So at this point, okay, the hysteresis loss directly proportional to okay frequency, and whereas eddy current loss directly proportional to square of the frequency. So if we remove the proportionality constant, hysteresis losses is equal to A into F, and whereas eddy current loss is a that is equal to the B into F square values here. So therefore iron losses is equal to the hysteresis loss plus eddy current loss. So how do we get these iron losses? Iron losses is equal to so AF the plus the BF square. So these are the iron loss. So if the B maximum is constant. Suppose in case of the case 2, so here the this is the case of view. So if the B maximum is not constant, okay, this is a B maximum is not constant, then what will happen here? So if the B maximum is not constant, so already mentioned this, the hysteresis loss directly proportional to V1 power 1.6, the F power zero point 0.6 here. Whereas eddy current loss directly proportional to the V1 square. Okay, V1 square. So now if you remove this proportionality constant, so therefore you can get A into V1 power 1.6 divided by the F power zero point 0.6. So these are eddy current losses is equal to B into V1 square. Now simplify here the calculate iron losses here. So this iron loss of the transformer, okay, iron loss. So that is equal to Wi. So is equal to WH plus WE here. So therefore iron losses is equal to so A into the V1 power of 1.6 divided by the F power 0.6. So that's the B into, so that is V1 square. So what about here? A and B values. Okay, A comma B are the proportionality constants. Okay, proportionality constant here. So this is the A and B one proportionality constant. So complete this iron losses during operation of the transformer. Joseph, all of it clear? Here I have taken simply the case one point of view. What will happen? So during the operation, this is the formula. Okay, clear everyone? So eddy current loss directly proportional to the B maximum square and F square. This is in the L. Suppose here I have taken the case 1. Okay, this is the case 1 here. So assume if the B maximum is here, B maximum, sorry, it is the case 2. Let us take B maximum is not constant. So this one is the B maximum is constant here. If the B maximum is constant means what will happen? Here eddy current loss directly proportional to F square. So if the B maximum is not constant means so that this value here, okay, this is the eddy current loss. Okay, simply assume here this is the B maximum square. It is the 1. Okay, this is the equation 1 and equation 2. Now substitute the equation 2 in the equation 1. You will get eddy current loss directly proportional to V1 square. Suppose total iron losses are required. Suppose this is a total iron loss. Total iron losses during operation. So this if B maximum is constant, Stark's law directly proportional to the frequency, whereas eddy current loss is directly proportional to the square of the frequency. So if remove this proportionality constant, you will get iron losses is equal to the AF plus BF square. And in the here, if B maximum is not constant, this is the formula for the Stark's loss and eddy current loss. So if you remove these proportionality constants here, the A and B comes, so that iron losses is equal to A into, so it is A into B power 1.6 plus B V1 square. All of it clear, everyone? So this is about complete the eddy current loss. What is the reason to get the eddy current losses, and also what is the reason to get the eddy current loss, and another one is what is mean by eddy current loss in the magnetic core, and formula to calculate the eddy current losses, and observations from that equation. This is a very important for problem solving. Any doubt? So third losses we will discuss, that is a stray load losses. Stray load losses of transformer. Okay, listen. The stray load losses are two types. Okay, these are the two types here. So one is a stray load copper losses. Okay, first one. So this is a first one is a stray load the copper losses of the transformer, and second one is a the stray load iron losses. Okay, it is the stray load iron loss of the transformer here. So what is the mean by stray load copper loss? Suppose example point. Okay, what is the meaning of the stray load copper loss? Okay, first point we will discuss. So that is the what is the meaning of stray load copper losses here. So stray load copper losses means, so always suppose here this is the one solid conductor we have taken as a So this is a one solid conductor here. So what will happen? Current passes through this conductor. So here some current here passes through the conductor's line. Okay, this is the current passes through I amount of the current. So passes through the conductors. Okay, here. So always I already mentioned that. So a current carrying conductor produces magnetic field around it. All of you clear point? So now this is a current. So this will produce a magnetic field. Okay, magnetic field. The around it. Okay, like. Okay, this is the around it. So now this is a the sometimes we can call it as a, so here this is the leakage flux. Okay, due to current. Okay, this is the leakage flux one. So due to here flux is there, conductor is also there. So therefore small amount of EMF induces, which in turn produces circulating current. So that circulating current within the conductor, the circulating current within the conductor. So this is a circulating current within the conductor. Circulating current like within the conductor. So now it is nothing but eddy currents. Okay, eddy current. So within the conductor, within conductors here. Okay, these eddy currents, the here power loss due to these eddy currents is known as the stray load copper losses. Okay, here completely here. So this, how do we define the stray? Shall I repeat once again? So first one, let us take one solid conductor. Okay, this is the solid conductors here. So whenever current passes through the solid conductor, so there is the some current here. This current carrying conductor produces magnetic field around its. So there is a magnetic field leakage flux, and also conductor is there. There is a EMF, which in turn produces circulating current within the conductor, as like circulating current within the core. So these currents are known as eddy currents within the conductor. So power loss due to this eddy current within the conductor is known as, that is the simply the power loss in the form of heat, in the form of power loss due to eddy currents, eddy currents eddy currents within the conductor, within conductor, within the conductor in the form of the heat, in the form of heat, in the form of heat is called, okay, the here this is the stray load copper losses, stray load copper losses. Got it fine? So here the stray load copper losses means additional I square R loss. Okay, this is sometimes also called additional I square R loss present in the conductor due to leakage flux here. Okay, this is the main reason to get the stray load copper loss here. Whenever leakage flux links with the conductor, the EMF induces, which in turn produces circulating current. So this circulating current in the here, the power loss due to this circulating current in the form of heat is known as the stray load copper losses. Okay. Yes, that is the skin effect only. Here, this is similar. The skin effect concept we will study in power system. They are similar to skin effect. All of you clear my point? So stray load copper losses means additional I square R loss. Additional I square R loss present in the conductor. Present in conductor. Present in the conductor due to stray currents or eddy currents. Due to stray currents. or eddy currents. Eddy currents. Okay. So this is the meaning of stray load copper loss. All of it clear, everyone? Now next one, stray load iron loss. Second one is the stray load iron loss. So iron parts are two types in a transformer. Iron parts. Okay, these are the two types of the iron parts. So first iron part is one is a main iron part. Okay, it is main the iron parts. Okay, second one is auxiliary iron parts. Okay, this is the auxiliary iron parts of the transformer. Okay, and main iron parts is the transformer core. Okay, these are transformer core. So now auxiliary iron parts means, so that is just like a transformer main tank. Okay, here the main tank. So that is the auxiliary iron part. So whenever here in this case leakage plug, which plugs is links here, mutual plugs. So whenever mutual plugs links with the transformer core, the here some currents, eddy currents in the core. So due to these eddy currents, power losses occur. That power losses are called eddy current power losses. But what will happen whenever the leakage plugs links with the auxiliary iron parts of the transformer? Some amount of power losses takes place due to eddy currents. So that power losses is known as a eddy current, the stray load iron losses. Okay, all of you clear point? So that is a whenever, okay, whenever, so this is a leakage flux phi L, okay, leakage flux, the links with auxiliary iron parts, links with auxiliary iron parts, okay. So eddy current, the auxiliary iron parts, some small EMF, small EMF, will be induced, which in turn produces circulating current. Okay, power loss, these power loss due to this circulating current is called which one? Yes, stray load iron loss. So this is the meaning of stray load iron losses. Okay, all of you clear my point? What is the stray load copper loss and stray load iron loss? Sometimes we have a question. So stray load copper losses. Okay, this is a note. Okay, here note first one. The stray load losses depends on the leakage flux. Agree point? The stray load loss depends on the leakage flux. Leakage flux depends on the load current. So that the stray load loss, what we conclude, is it a variable loss or constant loss? Agree my question? Stray load losses, complete copper loss and iron loss, stray load copper loss and iron loss depend on the leakage flux. But leakage flux depends on load current. So that what we conclude here, is it constant losses or variable losses? Tell me, variable losses. Okay, why? Because here stray load loss depends on, okay, first note, the stray load loss depends on load current. So it is a variable loss. Okay, variable losses. Okay, so next one more question here, order of the stay load loss. Sometimes we have a question here. Very good. All. So this is the order of stray load loss. So this is equal to 0.5% of total loss. Total loss. So that's why it is treated as the minor losses of the transformer. These are the two important notes. Okay, one is stray load loss depends on the load current, so that it is treated as variable losses. And here order of the stray load loss in the transformer, okay, in the transformer, so that is equal to 0.5% of the total loss. Okay, clear? And next one, fourth losses, that is a dielectric losses. Electric loss of transformer. Very good. That's correct. Dielectric loss of transformer. So how do we occur the dielectric losses? There are the three questions in the competitive exam. One is what is mean by dielectric loss? Okay. And whether these losses are variable loss or constant loss. Okay, like this type of question. And next one, order of the dielectric loss. Okay, these are the only three questions. What is the mean by dielectric loss? Whether these losses are variable losses or constant losses, and order of the dielectric loss. So how do we define dielectric losses? Let us take one example. Suppose this is the example point. So we have a transformer. So that is the 400 upon, or this let us take this example point 400 the kV here. This 400, or let us take, that is an example of, that is a 33 by, okay, 33 kV divided by 11 kV the transformer here. Okay, 11 kV transformer. Suppose here there is this is called as a HV winding of transformer, and 11 kV is called LV winding of transformer. So LV winding and HV windings are insulated by some amount of the insulation. So now this is the LV winding and HV winding. Suppose this is the HV winding and LV winding here. So what will happen? This simply two conductors are, okay, two conductors are the separated by the dielectric medium. Okay, this is the dielectric medium. So now here this is separated by some dielectric medium here. So this is the dielectric insulation between the two conductors. So what will happen? It is a similar to, okay, so similar to the capacitance, okay, capacitance effect here. So now here two conducting plates are the separated by the dielectric medium. So that's why what will happen? Small amount of the charging current flows through this the insulating material here. So this is known as, okay, power loss due to this due to the insulating material is known as the dielectric losses. Okay, how do we define here? Dielectric loss, okay, electric loss, the occur in transformer core. So due to insulating material, the insulating material which used between HV winding and LV winding. Okay, so this is the definition of the dielectric loss. Okay, all of you get it? So next one, now tell me, is it depends on the load current or constant? Now is it constant losses or variable losses? Is it constant losses or variable losses? Constant. Why? Because here is a independent of dielectric loss independent of the load current. Independent of load current here. So treated as constant loss. Very good. So next one, another question, order of the dielectric loss. Order of dielectric loss. So it is also very small. So that is equal to 0.25% of total loss. Total loss of the transformer. So this is the complete discussion about the losses of transformer. First one, in the losses lecture number 1, we are discussed about the copper loss. Lecture number 2, eddy current, the hysteresis loss. Lecture number 3, we have discussed about eddy current loss, the stray load loss and dielectric loss. All of you clear my point? Everyone. So now solve this question. First question number 1. Okay, if transformer is operated by keeping applied voltage constant, and frequency reduced below its rated value, then hysteresis loss and eddy current loss of transformer would be respectively. Okay, options are given like both are increased. Okay, option B, one is increase and decrease, and option C, both are one is decreases, other one is increase. Like so, next option D, both are decrease. Now tell me. Why? Because here it depends on the potential difference between. Okay, this is the C. Let's see here. So this is the potential difference between the LV winding and HV winding. So that is equal to, so 33 minus 11, it is equal to 11 kV. So 22 kV. So to withstand this 22 kV, we have to provide the insulation. Okay, here insulation here. So here the insulation requirement depends on the applied voltage, but not the load current. So that's why it depends on the applied voltage, but not the load current. So that's why it is treated as a constant loss. Okay, Joseph, are you clear now? Both reduces. The transformer is operated by keeping applied voltage constant, frequency reduced below its rated value, then the hysteresis and eddy current loss of the transformer would be respectively. First, yesterday we have discussed some questions. What we have to do here? Verify the B maximum initially. Verify maximum value of flux density, whether it is a constant or variable. Okay, here first one is a verify B maximum, whether it is constant or variable. So during operation, B maximum directly proportional to V1 by F ratio. V maximum is here. What is given? Applied voltage constant. The frequency is reduced, so that B maximum is will be increased. So B maximum it is not constant. When B maximum is not constant, so we know that when B maximum is not constant, the is not constant, so that hysteresis loss the directly proportional to, okay, directly proportional to v1 power 1.6, eddy current loss directly proportional to f power zero point 0.6. And what about the eddy current loss is directly proportional to the v1 square, okay, e1 square. So that this is a the in this case suppose option I have given, so one is increase and constant, okay, like what is the answer here? The in this case frequency voltage is a constant, okay, voltage constant, okay, frequency the reduce, so then hysteresis losses will be increased. So by keeping voltage constant, okay, therefore eddy current losses will be constant. So that what is the answer for this question? The hysteresis losses will be increase, okay, increase, and eddy current losses is a constant, remain same. Right, that's correct. Okay, now we can solve another question. Question number 2. If transformer is by keeping operated transformer is operated by reducing applied voltage along with frequency such that V1 by F ratio constant. F ratio constant, then hysteresis loss and eddy current loss would be, okay, same options, okay, find it. This one, option A increase comma increase, option B both are decrease, option C one is a increase and decrease, option C decrease and increase. Transformer is operated by reducing applied voltage along with the frequency such that V by F ratio constant. So then what will happen? Hysteresis loss and eddy current loss. Both are decrease. Very good. So first verify the B maximum. Here given that V by F ratio constant. So we know that here first what we have to do here? So verify the flux density. Verify the B maximum. How do we verify? During operation, okay, operation of the transformer, B maximum directly proportional to V1 by F ratio here. So as B maximum is as V1 by F ratio constant, okay, V by F ratio constant, the B maximum is constant once. Okay, when B maximum is constant, as B maximum is constant, so then the hysteresis loss so directly proportional to the frequency, whereas eddy current loss directly proportional to square of the frequency. Now here both are given that voltage reduce and also frequency reduce such that V by F ratio constant. When voltage is a reduce, here frequency is reduces, it starts losses will be reduced, and as the frequency is reduced, eddy current losses will be reduced. So that what is the answer for this question? Hysteresis losses will be reduced. Okay, this is the will be reduced or decreased, and eddy current losses also will be reduced. Both are decreased. Very good. Okay, all of you clear my point? So now let us solve one more question. A single phase 50 hertz 400 upon 200 volts transformer has hysteresis loss of 120 watts and eddy current loss of 100 watts when excited with rated voltage excited the high voltage rated high voltage and rated frequency. Okay, got it? So if same transformer is operated at reduced supply voltage of 300 volts 40 hertz then the new iron loss of transformer would be dash. Now answer this question, all of you. It is a numerical answer type question, NAT. Numerical answer type. Okay, first what we have to do, verify the flux density. Any problem is given based on the hysteresis and eddy current loss, whether B maximum, verify the maximum value of the flux density, whether it is constant or variable. If it is a constant, it belongs to case 1. If it is a not constant, it belongs to case 2. Okay. This is a, so how do we solve this question? It is a first given data is 400 upon 200 volts transformer 50 hertz. So that is the hysteresis loss WH1 is equal to 120 watts, WE1 is equal to the 100 watts. Okay. So supply is given to high voltage side. So that is the high rated voltage side. Now same transformer is operated with a 300 volts and 50 hertz, sorry 40 hertz 48. So then the new iron losses Wi2 is required. So now let us verify the B maximum. So verify maximum value of B maximum here. How do we verify? Okay, B maximum directly proportional to V1 by F ratio. So this you can write B maximum 2 is equal to B maximum 1. The multiplied by V12 divided by V11 into F1 by F2 values. Okay, F1 divided by F2. Now substitute the given values in this equation. So we know that the what is the relation between the B maximum 1 and B maximum 2. V12 is that is a 300 divided by 400 volts. The F1 is a 50, F2 is a 40 hertz. Now B maximum 2 is not equal to B maximum 1. So B maximum is not constant in this question. So now therefore, so we can find out when B maximum is not constant, okay, is not the constant. So that how do we write when B maximum is not constant? So that is a hysteresis loss, the directly proportional to V1 power 1.6. That is a frequency inversely proportional to zero point 0.6. Now similarly, the eddy current loss directly proportional to V1 square. How do we calculate this? The WH2 is equal to WH1 multiplied by V12 divided by V11 whole square, V11 power of 1.6. The frequency the inversely proportional, so that F1 by F2 0 0.6. Now substitute these values, you will get the WH2. Similarly, WE2 is equal to the WE1 into V12 divided by V11 whole square. So therefore, WH2 is equal to WH1 is given 120. So the here V12 is equal to 300 upon the 400. So power of 1.6. It is a 50 divided by 40 power of 0 0.6. So now WE2 is equal to, so WE1 is 100 into V12 is equal to what is the value of V12? 300 divided by 400 whole square. Now simplify this. The WH2 is equal to, can you tell me WH2 here? Okay, calculate and tell me this WH2. Can you tell me WH2? Calculate, and also WE2. What is the WH2 is equal to? 86.58. Okay, this is the 86.58 watts. Very good, Siddhant. Next one, this one, 0, 0, that is a 9, 16. So that 9 by 16, it is equal to 56.25. 25 watts. So therefore, iron losses 2 is equal to WH2 plus WE2, the is equal to how much, this value? Okay, so this value is equal to 86.58 plus 56.25. Okay, 25. So it is equal to 142.83 watts. Okay, this is the answer for these questions. Very good. All of you got it? 142.83 watts. Can you solve one more question? Okay. Can you solve this question also? Solve here. So that is a single phase 50 hertz 400 upon 200 volts transformer. Transformer as hysteresis loss of 120 watts and eddy current loss of 100 watts. When excitation given to, okay, high low voltage side at rated voltage and rated frequency. Rated frequency. Got it? So if the same transformer is excited with 160 volts 40 hertz 40 hertz, then the percentage reduction in hysteresis loss and eddy current loss. Okay, now calculate this question. Percentage reduction in the hysteresis loss and eddy current losses would be, calculate. Okay, any question given based on the losses, the first thing what we have to do, verify the flux density, whether it is constant or variable. Once you know that, then we can answer the question easily. Without verification of the flux density, don't start the question. Okay, got it? How do we answer this question? So that is a 400, the given here 400 upon 200 volts 50 hertz. Hysteresis loss WH1 is equal to 120 watts. WE1 is equal to 100 watts. Okay, this is given data. So next one, supply is given to which side? LV side. Okay, at rated voltage and rated frequency. So next one, same transformer is operated. So with the reduced voltage of 160 volts 40 hertz. So then the new iron loss, sorry, percentage decrement the in hysteresis loss and eddy current loss. This is the question. So first verify the B maximum. Verify B maximum one. So we can verify here like this also. B maximum directly proportional to V1 by F. So this is equal to V11 by F1 is equal to V12 by F2. So if this ratio is a constant, then we can say that the constant value V11 by F1 is equal to the 400 divided by 50. So this is equal to, sorry, 200 divided by 50, 160 divided by 40. So here therefore V by F ratio constant. So if V by F ratio constant, the B maximum is constant values. Okay, like this also you can verify the B maximum, right? So after getting the B maximum, then we can find out the hysteresis loss. So when B maximum is constant, okay, constant value, constant, how do we answer this question? So when B maximum is constant, hysteresis loss directly proportional to the frequency. So that is equal to WH2 divided by WH1. So instead of writing here, I am writing WH1 into the F2 divided by F1. Okay, F1 1. So when B maximum is constant, this one. And WH2 is equal to, okay, WH1 is a 120, the into F2 is equal to how much? Okay, this value F2 is the 40 divided by 50. So now calculate. So this value is equal to WH2. Otherwise, you can write directly here. So this is a, so that is a WH1. So now this is equal to 0. WH2 is equal to 0.8 the WH1. Okay. So now we required percentage reduction in the hysteresis loss, right? In hysteresis loss, so that is equal to, by using this also you can answer, otherwise you can calculate WH2 divided by the WH1 multiplied by 100. So this, the reduction value is required, that's why we can write, so that is the WH1 minus 0.8 WH1 divided by the WH1 into 100. So it is equal to 0.8. Okay, 0 point, the 1 minus 0.8. So this is equal to 0.2 into 100, it is equal to 20%. Okay, this one. So next one, when B maximum is constant, okay, then what will happen? When B maximum, okay, when the B maximum is constant, eddy current loss directly proportional to, okay, frequency square. Okay, here, so this is the WE2 is equal to WE1 into F2 by F1 whole square. So now simplify here, WE1, F2 is a 40 divided by 50 whole square. So that is equal to, that is a 0.64 WE1. So therefore percentage reduction is equal to WE1 minus WE2 divided by WE1 the into 100. So that is equal to how much? 0 WE1 minus 0.64 WE1 divided by WE1. WE1 is a common, so that it is a cancelled out. The remaining, it is equal to 36%. 36 point, this is a 36% exactly. 20 and 36%. Okay, this type of question will ask in competitive exam. Tomorrow we will discuss every question based on the losses, previous gate questions, previous IES questions, all type of questions based on the complete losses of the transformer concept. Tomorrow is a very beautiful class. Can solve any type of question based on the losses by attending tomorrow class. Okay, all of you please share these videos to all the students, and only the share it in your WhatsApp groups, and also share it, keep this video as status of your WhatsApp. Yes, tomorrow also you have a special class, that is a questions based on the special class concept is a, okay, tomorrow we have a special class that is a previous year questions based on the basics of the transformer, all type of question part. I will concentrate more on the question, that's why I'm taking special class based on the questions. Okay, Nageshwar, Pavan, Bhargav, okay, all of you share this video to all the students, to reach all the students. Okay, tomorrow special class timing is same 11:30 to 12:30. We will discuss the questions part, complete transformer questions. The different type of questions we will discuss here. Okay, any more doubt? Pavan, Nageshwar, share these videos to all your friends. Siddhant, keep this video status of your WhatsApp. Siddhant, Isha. Okay, So this is the official creatrix channel. Okay, please join in this channel to get any updates from the creatrix. So this is our Telugu channel, Telegram channel. Here Unacademy Gate Telugu. Here you will get all class notes PDF, and these are under Unacademy some channels like one is a creatrix Gate, Unacademy Gate Mechanical, Unacademy Gate Civil, and this is our channel Unacademy Gate Telugu channel. Okay, please like the channel. Okay, and also share it that to the maximum people. And next one, subscribe this channel to reach all the people here, or subscribe to get all the notifications from the channels. Okay, thank you all. So tomorrow we have a special class based on the questions. In the special classes we will discuss the question part, complete question bank based on the single phase transformers. After that, we'll discuss three phase auto transformer. Next one, DC machine. Okay, suppose you are going to write the gate 2021, it will be useful. So that is in the Unacademy app of special class. Okay, Joseph, Unacademy app lo special class ఆ టైమింగ్ ఏంటంటే 11:30 to okay 12:30 exactly. మా ఈవినింగ్ we have a class same continuation machines class from okay regular machine class. Okay, that is from the 4 to 5:30 or 6, like depends upon the topic. In the Unacademy there is a special class. Okay, that is a we will discuss all type of questions based on the single phase transformer. Thank you all. We'll meet tomorrow.